Hey everyone, we're gonna start in just a couple minutes here. Yeah, so just hang on a couple minutes and we'll be right on our way. So maybe like 2 minutes or 3 minutes or something. Right. Hey everyone. All right, I guess let's get started. Right, I think it's about time. All right then. All right, so first things first, we're going to go through the attendance. I seriously have to apologize to you guys. So from the last 2 weeks, I've kind of noticed that my internet connection and Blackboard Collaborate don't seem to get along too well for whatever reason. So I will ask that once I call your name, can you text in the chat box that you guys are here, instead of opening up your mics, because I found that because of the mic, sometimes I get cut off because of that. So sorry about that, guys. And of course, I will be available on chat entirely. So another thing I found out is that my phone seems to not hang. I guess it's because of the presentation or something that with my laptop hangs, my phone doesn't hang. So I'm gonna be present in the chat as both Said Ahmed, the presenter, the host, right, and also as a like Said Ahmed number 2 is going to be my second one. That's also me in case something happens with my laptop, so that we can always stay in touch and I don't get cut off. Hopefully, right. All right. So when I call your name, please, text your here, right? So Jotham Abraham. Okay, here we go. Muhammad Ali. Okay. Sanya Anil. Sanya. Sanya. Oh, there. Okay. Sorry. Uh, um, Huang Bui. Okay. Zayma Anam. Sorry. Zaina Anam. Zhao Fang. Yanling Liang. Okay. Anjali Mahidio. Argavan Majidi. Okay. Jia Mi. Jordan Moran. Okay. Zinal Patel. Alia Pathan. Okay. Judson Sarviswaran. Asmi Shukla. Okay. And lastly, Persan Shah Singh. Okay. All right. With lab attendance out of the way, I guess we can now continue with the rest of the presentation. All right. Oh, before I continue, so I also noticed that when students start asking questions and so on in the middle of the lab, sometimes it also causes my laptop to freeze. So if you have any questions, feel free to text it, and I'll respond right away, from either Sayyid Ahmed or Sayyid Ahmed number 2, whichever one is working better at the moment. I have my phone right here available, and you can do that, or you can email me after the presentation, right? So after the lab, I will be available, and I will be available via email, and I will answer all questions in detail. I'm not even going to count office hours or anything, because this is totally not your fault at all. This is entirely between me and Blackboard. Right, so feel free, email me. I will answer any questions. Make sure if you email me, though, to include B41 in the subject line of the email, and the lab number, and practical number, so that I can find you later on, because maybe I see the email when I'm out. Sorry. If I see the email when I'm out, then I can always remember and come back to it. Sorry. Okay. All right. So learning goals of this lab. So this is a pretty easy lab as far as labs go. This is about recrystallization, and so there are three learning goals. Sorry. So there are three learning goals. Number one, to understand the principles of recrystallization. Number two, to be able to purify an impure solid using recrystallization techniques. And number three, to identify and comment on the purity of a given compound based on its melting point. Right? And we're going to talk about this a little bit, but melting point is not a point, it's a range. You're going to be given two numbers, right? And you're going to have to record both of those numbers. So we're going to talk about that a little bit. All right, some background. In the previous experiments, we noticed that, last time on Chem B41, we separated our carboxylic acid and neutral compounds, right? And we were able to go from there, and we now have two different compounds that we have dried over the course of the last 2 weeks. And now we want to recrystallize. Some of you guys have come and asked me, your yields or whatever, what happens if they're over 100%? Well, that's okay. If you had a yield of over 100% in a crude separation, right, then it just means that there's some impurity in there, some impurity or another, right, that got trapped in there. And that's okay for your crude. But now you're going to recrystallize, and you're going to get highly purified samples. Right? Now, a couple of questions just to kind of remind us and get those juices flowing. Right? What was used to separate the acid? How? Right? If you guys remember, we used sodium bicarbonate and sodium hydroxide and sodium bicarbonate to kind of get the carboxylic acid separated. And the neutral compound, how did we separate that? Well, it's a phenolic neutral compound, so we used NaOH, and the remainder was in the organic ether. Right? Alright, moving forward. So, theory on recrystallization. So, there's a lot of things in this slide, and I really want to highlight a couple of them. Can you guys see my mouse? I hope you can see my... Okay, yeah, perfect. Excellent. Good. Thanks, guys. So... recrystallization, important technique for purifying non-volatile organic solids. Right? Separation allows us to distinguish, separate the two compounds. Recrystallization allows us to remove any of the impurities that we got when we separated. Right? And we get only one compound in there, or hopefully only one. Right? And now, knowing the solubility of most solids that increase at high temperatures, the solute to be purified is dissolved in a hot solvent. Right? So, okay, and this will make a lot more sense as we go to the lab. But first, what you do is that you use a hot solvent to dissolve all of your compound, and then it crystallizes out of the solvent. Right? And the recrystallization solvent is selected so that the desired compound is soluble at high temperatures but not at low temperatures, right? Or minimally soluble at low temperatures, right? Or room temperature, I guess. Yeah, room temperature, because we're not going to freeze it so much. But absolutely. And the reason for that is because you want it to dissolve when you heat it up, but you want it to come out of solution once you cool it down. But you don't want it to, have to put it at like minus 200 degrees in order to get it out. You want it to just come out easily at room temperature. Right? So you got to choose the solvent for that. And we'll talk about that a little bit later. Alright, so what are the desirable characteristics of a good solvent? Well, there are 5. One, it should dissolve the impurity readily in hot solvents and very little at room temperature. 2, it should be insoluble. Yeah, I guess that's 1 and 2 are the same. Not the same, but I said them in one go, sorry. 3, should yield well-formed crystals of the purified compound, right? And should be easily removable. It doesn't make any sense to have well-purified crystals, but then you can't remove them from the solvent. They're just stuck in there. Right, so it should be easily removable. Number 4, should not chemically react, because we want to remove and isolate our compound, right, in its purified state. We don't want to turn it into a new compound. And number 5, it should be inexpensive and of low toxicity. And I think those just that just speaks for itself. right? And here, colored impurities in the product should be removed using charcoal. So charcoal basically gets absorbed onto, like, any impurity, colored impurities will get absorbed onto the surfaces of the charcoal, and then you can remove the charcoal during gravity filtration, and you basically remove all of the colored impurities. Um, Now, this would actually, I think, make a little bit more sense in the lab when you do it, but then you'll see kind of what it means. Lastly, crystal shape. So pure crystals can have multiple shapes. You can have rings, you can have needles, you can have orthorhombic, you can have platelets. So a couple of different needle types, a couple of different crystal types exist, but generally speaking, most of yours are going to be needles or platelet kind of shaped compounds in B41 and B42. But anyways, there are more types, and you should be aware of what they are. And I'd highly recommend each of you, after the lab, to kind of just make a note on the side right now, and after the lab, go in and see what an orthorhombic crystal looks like. What should you look for? Right? Needles are pretty straightforward, long, thin. All right, theory on melting point. So melting point is the temperature at which the solid is at equilibrium with its liquid phase at atmospheric pressure, right? So, but that basically means it's the point, or it's a temperature at which a solid is just in the transition between solid and liquid at 1 atmosphere pressure, right? Now, prior to measuring the melting point, the calibration of the thermometer is done. So basically, just think of it this way. If you're ever going to use an instrument to test something, you want to first make sure that instrument works, right? And it's working properly. That's just what calibration means, right? And then you want to also get a melting point. So when you put it in the instrument and you test it and you start it, you want to set it to raise the temperature by 1 or 2 degrees centigrade per minute, and you want to get the melting point as a range. Now, the reason why you want to go only 1 to 2 degrees Celsius per minute is because you don't want to go too fast. Like, for example, let's say your melting point is 85 and you go by 10, right? Then you're going to get 0, 10, 20, 30, then 70, 80, 100, right? It's going to be very difficult to get that 85 range in there, right? So that's why. You want to go by something small, incremental, that gives you high accuracy, right? And of course, the melting point is given as a range. I mentioned that before, right? You want to get when the first part of solid starts to melt, right? Begins to melt, and then the last number is when the last solid turns to liquid. Right, those are the two melting point extremes. Right now, if you do know the melting point of a sample, so let's say you know it's 85, starting off at 0 degrees, right? Like I mentioned in my example, and going up by 1 or 2 degrees per minute. Well, obviously, you can just do the simple math, right? Like 85 divided by 2 degrees per minute is going to give you like 40 minutes. That is far too long. That is not a good choice. So you want to ramp up quickly to like 70, and then from 70 to 90 or something like that, you want to do 1 to 2 degrees per minute. Does that make sense, guys? I hope so. Make sense? All right. Excellent. Okay. So yeah, if the sample is pure, the melting point range would be very narrow. So let's say one of our compounds has a melting point range of 85 degrees Celsius. Right? So what should we expect in the melting point range? We should expect, 84 to 86. Okay, that's very reasonable. But if we see like 82 to 88, that's not pure. Something is wrong. And then the presence of impurities. So anytime you see a range like that, like something huge, like 83 to 89 or whatever I said before, right? And you see that it's very wide, that means there are impurities present, and they oftentimes also decrease, well, they will decrease the melting point of the compound, of the pure compound. Right? And if you have a mixture of two compounds, then one of them acts as an impurity in the other. Or if they're in equal quantity, they both act as impurities to the other. Right? So, yeah, that's the theory on melting point. Let me know if you guys have any questions. Awesome. Then for the sake of time, I think we'll move forward. Lab skills videos. You guys are highly encouraged to view the lab skill videos. I'll post the links in the chat just in case you haven't got them. Just 1 second. Okay. Alright, so strongly encouraged to watch those in your spare time. Alright, let's begin our lab. So, recrystallization of a carboxylic acid. So, here we go. If you see at the very top here, yep, there's my mouse. So, at the very top here, we have 3 different Erlenmeyer flasks, right? And then we have a hot plate. So, one is called Erlenmeyer 1, Erlenmeyer 2, Erlenmeyer 3. Now, flask or Erlenmeyer 1 is has the impure acid, 7 mils of water, and some boiling chips. You can kind of see it down there a little bit. If you squint a little bit, you can see it. Right? The boiling chips. Right? Erlenmeyer 2 has 50 mils of water, boiling chips, and a ring clamp. Right? And the fluted paper and the funnel are actually on the ring clamp. It's a little bit hard to tell. Right? And the purpose of this, by the way, is to keep everything moist. So once we do gravity filtration, we want to keep the funnel and the paper moist and warm. Otherwise, you'll start getting premature crystallization on the actual filter paper, and you're going to lose everything. Right? So you have that. And number 3 is 50 mils of water, boiling chips, and a glass dropper. So I guess actually this is number 3. Oh, yeah. This is 3. This is 1. I don't know why it's backward. Sorry, guys. This is 3, this is 1, right? Number 3 has the glass dropper and stuff like this. So basically what you're doing is we have our compound, we want to move it in, and we want to add it dropwise until all of our solvent dissolves, right? So as you can see in the second shot here, right? So when we have our compound, we want to add little by little until all of it dissolves. So we have all hot solvent, none of it is cold. So in hot solvent, we try and dissolve it, and we add very, very small portions from flask 3 to flask 1 until it's completely dissolved. Once it's completely dissolved, then we add more solvent. So here's the kicker. This is important, right? You dissolve all of it, then you add 25% of the total volume more. So, saying this in numbers to make a little bit of sense. Let's say it took you 100 mils to dissolve it. It will not. It will not take 100 mils to dissolve it. But let's say for easy math, right, it took 100 mils to dissolve it, right? Because 25% or 1/4 of 100 is 25 mils. So after you dissolve it in 100 mils, you will add another 25 mils. Does that make sense? Right? So here's a question for you guys. Why? Why add the extra 25 mils? Oh, okay, yeah, a little bit difficult to answer. But I'll answer for you guys for now. And, oh, yeah, okay. Alright, so basically, yeah, the purpose of adding the extra 25% is to kind of prevent premature crystallization as soon as you take it off. Because if you add only just enough, then the moment a small portion of solvent evaporates, it's less than just enough now. Right, so you don't want it to have premature crystallization coming out, so we add a little bit extra just to keep everything in solution. Right, and then everything is still boiled. Then from the hot plate, you cool. Then once everything is boiling and dissolved, you've added your 25% extra. You take it off the hot plate, and then you let it sit at room temperature for a while. You do not add it directly to an ice bath. Never do that. Never go straight from hot plate to ice bath. Bad idea. So, and the reason for that is because if you go directly from hot place to ice bath, what's going to happen is that it's going to cause a shock, a temperature shock to the glassware, right? Now, although our glassware is great, but if it's too fast, it can cause breaking. Not only that, but if the temperature changes too fast, as you get even if you leave it at room temperature, you'll start to see crystals form. But if the temperature change is too rapid, you're gonna get premature crystallization, and it's gonna be very, very tiny amounts of small crystals. You won't get to see the beautiful crystal shapes. And honestly, if you do it sometimes, you can just kind of press it and see, and you'll notice that you actually can see like long needle shapes. You can see the shapes of the crystals. It's not just something you look at. And again, highly recommend that you guys after the lab kind of Google crystal shapes and take a look at what you find there. Right? Alright, and to get rid of some of the charcoal, if you've added charcoal, right? So let's say you add charcoal, alright, because you had some colored impurities. To remove the charcoal, basically what you would do is that you would add just a very tiny spatula tip of charcoal into the compound. It'll absorb the colored impurities. Then you'd get an empty Erlenmeyer. You take the warm fluted paper and funnel, and then you would use that with the empty Erlenmeyer to pour your charcoal compound, so dissolved compound, in. The fluted paper will take out the charcoal, and then everything dissolved in the solution. It'll go through, and you'll still be able to work with it. Right? And yeah, there we go. Alright, procedure for recrystallization. So I have the videos here for you. Oh, sorry, 1 second. Wrong screen. So here we have someone, cleaning a hold on, sorry. I think 1 second. Oops. I think I might have opened the wrong video. Sorry, guys. Sorry. I'll just open it from here. Sorry, 1 second. I had them saved so that this wouldn't happen, and clearly I goofed up. Alright, here we go. There we go. So here we go. Here we have... Sorry. Okay, here we go. So here we have the ice bath, and we have our flask number 2. We have our compound. We're about to see the crystals in it. So you can see the nice crystal shape, and I'm terrible at this. There you go. You can see the nice crystal shapes. It's a little bit harder to see in the screen and via camera, but you can definitely see how you can see the needle shapes, right? Yeah, there you go. This is a nice image. So you can see the needle shapes of the crystals. Now, once it's at room temperature, we're going to also put it into an ice bath just to make sure we get all of it. Because as we know, it's marginally soluble at room temperature, right? But we also want to make sure that we get all of it, so we're going to cool it even below room temperature, right? And then we're also going to, whatever solvent we're going to use, in our carboxylic acid case, we're going to use ethanol. We want to cool that down too, so that when we do our filtration, we're going to wash it down with cold ethanol so that it comes out of solution and it doesn't dissolve back in. If we used hot ethanol, literally it would just dissolve back in. Right, so here we go. We have our setup. Before we continue, I just want to rewind this for a second about how they set it up and just kind of show you guys. So notice that they added they clamped the apparatus down first, then they added the vacuum tube. Right? You don't add the tube first. These are very thick tubes. They have a mind of their own. They literally will flip over, and you'll lose everything if you don't do it. If you don't clamp it first. Right? Then they add the Buchner funnel. They make sure everything is nice and tight. Right? Make sure everything's tight. Then they add the filter paper. Yep, there we go. They add the filter paper. Turn on the vacuum. Then they're going to wet it with some cold ethanol. Remember, not warm ethanol, right? And the purpose of this, again, is just to stick the filter paper against the bottom of the Buchner funnel. That way there's no air in between and you get an even suction. Right? Then you want to take your flask of your compound. Right. You don't want to break the crystals per se, but you still want to get them all out. So swirl to make sure you get them all into the solution. And pour. Right? You can see it goes through quickly. Remember vacuum filtration, one of the differences between vacuum filtration and suction filtration is that vacuum filtration is cold because of the vacuum of the suction, and gravity filtration is hot. And in vacuum filtration you're interested in the solid, the precipitate. In gravity filtration you're interested in the solution. Right? Once you are done and the crystals are nice and dry, you take it off, you put it onto a larger filter paper, right? And then you're going to pre-weigh a bag. Yeah, here we go. Pre-weigh the bag. I just want to point out, note the lab notebook is here too. They take the lab notebook to the actual weighing scale, and they measure, right, and they record right away. They don't try and remember the numbers. That's bad. You have to do it as you measure. Right, so they got the weight of the bag. Right, then they get the weight of the bag plus the compound. Oops, sorry. Right, so very simple procedure to get the amount. You just subtract the two, right? Weight of bag plus weight of bag plus compound gives, like, the weight of bag plus compound. Subtract the weight of bag, give you just the weight of the compound. Right, I hope that's clear. All right, recrystallization of the neutral compound. Right, it's exactly the same technique, except 95% ethanol is used. I mean, not even difficult. Right, so same exact process. You already have it in the solution. You just take it, set up the apparatus exactly the same way. You wet it with 95% ethanol, and you go from there. All right. So, melting point apparatus. So this is the melting point apparatus. This is what it looks like. Over here in the top, there are slots for 4 holes, and that's where you put the melting point capillaries. The capillaries are long, thin tubes, right? They're closed on one end, open on the other. What you're going to do, and this is, you're never really truly going to get it until you see the, actually, there's a video for it. Sorry, I'm going to show you guys the video. Here we go. So there's the apparatus. These are the capillaries I was talking about. Right, so you take the open end and you kind of jab it into your compound, trying to get something in. Right, wipe out some of the excess because otherwise it makes a huge mess. Then you drop it from top to bottom. Some students get confused. The tubes are closed on one end, open on the other. Think of it like a glass, like you drink from it, right? It's open on one end, closed on the other. The closed end goes to the bottom, the open end points to the top, right? And then when you drop it, compound moves from the open end to the closed end. Right? And then as it bounces, you'll see that it starts to move downwards. And we'll see an image of that in just a moment. There you go. See, you get like a tiny, tiny bit towards the bottom. That's all you truly need. You don't need much more than that. Right? Then you take it, you put it into the device. Usually the amazing lab technicians have it all set up for us, so we don't need to play around too much with the actual melting point range. They have it set so it's in a reasonable amount, but if you do know what it should be because you've done your pre-work, you can set it up yourself. So here we can see our compound I mean, it's not like an HD camera, but you can definitely tell what something is in there, right? And you'll be able to tell when it turns to liquid. Just watch. It's exciting. Sometimes I just stare at melting point tubes. I mean, you guys can never do that because I'm always yelling at you like, do this, clean that, do this. But, I mean, it's fun to watch. Did you guys see it? It's starting to melt. Starting to melt. Yeah? And almost gone. There we go. And then we have our benzoic acid. There. And I'm going to pause right there. If you guys want to maybe write down some of those melting point range, right? You got two numbers like we mentioned, 123.4 and 124.2. It's within 1 to 2 degrees, you know, very close, very, very close. Less than 1 degree actually. So we know it's highly pure, right? And then you can see the numbers for each of the 4 capillaries again in this thing, right? Biphenol. So this is crude. This is the crude, and this is the recrystallized. Just to give you guys a comparison of what happens and what the temperatures look like. Because I mean, when you look at the crystals, they both look like they're pretty decent. They're pretty pure, but melting point, it reveals the truth within. Look at that. Recrystallized is already gone at 69.8. $70.2. Alright, 69.8 and 70.3. You can tell it's only a difference of 0.5. Right? But even this one over here, 70.2 to 1.3, it's just 1.1 off, right? So you'd still think that's fairly pure. So I mean, but for biphenol, we did a pretty good job separating that means, right? It's still not, I mean, it's still not perfectly pure, but you can do better, like 0.5. But you can see how melting point changes things, or impurities change things. And again, you get the summaries over here. Right, crude has higher melting point range than does pure. Alright, once you get that, you will report it onto this data sheet, and we have a video for that. It's literally recording onto a data sheet. Right, open directly here. So this is what it looks like. The benzoic acid, look at the crystals, right? Notice notebook is next to the weighing scale, right? When you write everything down. So they're going to staple it together with their compound. So that's what happens, right? So you put down everything, you write down your theory. You're going to write down theoretical and actual yields as well. They're just kind of showing you what happened. They wrote down their melting point. You're also going to have literature melting point written down. You're also going to have expected color, actual color, and crystal form filled in here. Right? But this is basically what happens. It's like a small rectangular or squarular sheet that you staple with your compound. It has your name, student number, date, and product number on there, as well as all this other information. Right? And then you get marked on it. Right, so that was benzoic acid. Alright, biphenol. So it's exactly the same in terms of the paper and everything. It's just different values, and we'll see that here. Here we go. So you can see very different crystal shapes, right? You remember the last ones? You remember how they were like little platelets, almost needle-like? right? So very different. Stapled it together. Wrote down everything. Take a look at this amazing lab notebook while we have it open here. Right, you can see melting points written down, benzoic acid, biphenyl. They have the crude written, they have the purified written. Anyone can read this and know what's happening. Right, that's what's important. Yeah. And there we have it. That was your biphenyl compound. All right, some discussion questions. Okay, so again, sorry because of my internet. So we're gonna have to discuss over texting, and okay, I might kind of go through these a little bit. And if you have questions, feel free to email me. In a couple slides, I'll show my email again, and I'll text it now here actually. Right, and so you guys can just kind of find me. It's in a couple slides, anyways. Right, so and you guys can email me if you have any more details on these questions. All right, so why should a recrystallization solution be allowed to cool slowly, undisturbed, rather than quickly? Right, so if we want to take a second to think about it. Anyone have any ideas? Yeah, exactly. Yeah. There you guys go. Yeah. Sorry, I guess internet just lagged or something. Yeah, basically, recrystallization solutions. You don't want it to have premature crystallization, and you don't want to have impurities come out with your crystals, right? Because they can also precipitate out if it's too fast. Right? I think we'll just kind of go by these, and then we'll break you off into your breakout groups, and you guys can have more of a discussion there because I guess it's less of you and it's easier to talk. So what are the characteristics of a good solvent for recrystallization? We mentioned 5 topics, right? So, be soluble in hot solvent, be marginally soluble in cold solvent, easy to separate, not toxic. Forgetting one of them. Does anyone remember the 5th one? Should not react chemically. Yes, of course. Yep, 100%. Yeah, should not react chemically. You don't want it to react chemically. Yep, absolutely. Sorry, guys. Okay, so yeah. So why shouldn't you add too much charcoal to your recrystallization mixture? So now we're assuming that you have some colored impurities. So why should you just add like chunks of charcoal into there? Right. So obviously, if you add too much charcoal, it might absorb your compound. Right? So you don't want to lose yield, right? All right, and what is the meaning of depressed or lowered melting point? It just means that the melting point is lower. So for example, if we were looking for 6970 for one compound, a depressed melting point would be like 67, 68. Right? So lower melting point. All right. In conclusion, upon completing this virtual experiment, you have a better understanding of the theory and techniques of recrystallization to purify organic compounds. You should also have a reasonable level of understanding on how melting point can be used to identify and check the purity of organic compounds. Right? So, if it's off by more than 1 to 2 degrees, it's not so pure. All right. At this point, I'm going to break you guys off into your breakout groups. And then you guys are going to answer these questions. Do not answer these questions to me on the public chat. Some people made that mistake last time, so don't do that. Instead, I want you guys to. I'm going to break you off into groups. Then, one person in each group send me an email. CC all of your other group members. That entails that while you guys are discussing in your breakout groups, to get each other's emails and names, right? So know who each other are, right? And then. Send it to me using this title, Chem B41 _ lab 2, right? _ name 1, and then your group member names, right? And so the reason I've decided to go this way is because last time some people were telling me, and even the other group were telling me that maybe my internet cut out and I didn't get their answer, or something happened here, something happened there. So email is just a perfect stable way for me to always get the answer. And so honestly, I think it's the easiest way to go. Right. So I have my email written down right over here. My mouse gets on here. It is right. My email is right over here, so I'm going to give you guys a moment to write down my email. Right, hopefully you guys already have it, but write it down again. And just send me an email with your answer. My email can also be found if you go to Blackboard and then you go to like emailing groups and stuff. You can also just send our entire lab or just me an email. So you can also find it in more than one way. So do this and CC all of your group members. The reason why I don't say every group member send me an email is because then I'll have like 18 something emails instead of 4 or 5, and you're all saying the same thing. Alright, your 3 questions are: what is the purpose of recrystallization? Do impurities raise or lower the melting point? And why is melting point range? What is melting point range, I should say, and what do each of these values mean? Oh no, why is melting point a range? Wow. Why is it a range, and what do each of the 2 values mean? Again, my email and the lab title. Alright, breakout groups time. And I'm going to close my monitor, my webcam, because I think it's just going to increase lag at this point and nothing else. And the lab is now done, by the way, so once you're done with the breakout groups, feel free to head out. Okay, some should be coming in right away. If I can stop the presentation. I should have a thank you slide. Okay, I think that's plenty of time. I think time to stop.